Hi, I'm Ryan Baker, and this is Big Data Education. And today we'll present a case study in classification, Zhang et al. So, in educational data, nowadays there are thousands of examples to choose from. And this one is one that I know particularly well, which is the main reason I chose it. For another great example, an older one, see previous versions of this course. That's a good example too. So, this example comes from Zhang et al. Proceedings of the International Conference on Educational Data Mining 2022, Detecting Smart Model Cognitive Operations in Mathematical Problem-Solving Process. And like most contemporary work today, it's got a bundle of co-authors. The goal of the study was to build detectors that can infer behaviors associated with students' self-regulation. And this work was grounded in Winne and Hadwin's SMART model of self-regulated learning. Searching, monitoring, assembling, rehearsing, and translating. So, why would we want to build these detectors? Three purposes. First, to embed them in interventions that can make recommendations to students about strategies that they're not currently using. Second, reports for teachers on strategies that the whole class isn't using to recommend that the teacher emphasize them to the class. And third, to create asset-based reports for teachers on what strategies their students are using. And this is an important point. So much of educational data mining and learning analytics has been deficit-based, figuring out what a student isn't doing and saying, hey, you got to do this. These reports were designed instead to be asset-based, to tell teachers these are the strengths your students have that they can build on. The context, the CueThink learning platform, where students solve complex mathematical problems, record videos of their answers and their problem-solving process, and then critique each other. In our current study, we build automated detectors of SRL constructs from a theory-driven lens. So we take data from the CueThink platform, interpret that data in the lens of Winne and Hadwin's SMART model. And incidentally, CueThink was designed, using that model in mind. We label 5 indicators of students' self-regulated learning. We build automated detectors of those indicators, and then we investigate the performance of those models and check them for algorithmic bias. And incidentally, we're going to talk a lot more about model performance, algorithmic bias, and how to validate in terms of those in future lectures. So CueThink scaffolds a student through 4 phases of mathematical problem solving, which again is designed using Winne and Hadwin's model. The first, the understand phase, where students are prompted to try to understand the math problem they're working on. The second, the plan phase, where they choose strategies that they're going to use to solve the problem. The third, the solve phase, where they actually solve the problem and then create a video of it. And the fourth, the review phase, where the student checks their math, checks the recording, reviews an estimate originally, and provides a final answer, and then students critique each other. Our detector building process was as follows. We operationalized the constructs, the 5 indicators of self-regulated learning that we wanted to detect. We coded the data, hand-coded the data, to obtain training labels of those constructs. We distilled features from the interaction log data, and then we trained models. And then we validated them and checked them for algorithmic bias. So in operationalizing the constructs, we first took the SMART model, which, as you may recall, breaks down into 5 cognitive operations: searching, monitoring, assembling, rehearsing, and translating. And we focused on assembling and translating for this specific project. Now, we actually have had papers since then that detect more of these and knowledge engineering work to do so, but I won't focus on that for the moment. And we broke down assembling into 4 constructs and translating into 1. Within assembling, we looked at numerical representation, which has to do with the degree to which students are representing the number of quantities in the problem. We also looked at contextual representation, which has to do with the degree to which students took contextual information out of the problem to help them reason about it. We also looked at strategy orientation, which has to do with students' ability to create a plan based on specific strategies for how to find the answer, and outcome orientation, which had to do with the degree to which students thought ahead about what kind of solutions they might obtain and what kind of answers they might obtain, and specifically whether they were reasoning around their estimate of what the problem solution might be. In terms of translating, we looked at data transformation, which had to do with how students were engaging in transforming their data, the numerical quantities in the problem, to help them reason about the answer. Our next step was to obtain human labels as to these constructs. Our first step in this process was to first engage in some preliminary coding, more exploratory, where our human coders looked at the data and tried to see if they could identify these categories. We then had them engage in separate coding, where each of the two coders went off and coded the same set of clips separately, and then we checked them for inter-rater reliability. And finally, after they had achieved inter-rater reliability, we had them engage in individual coding until they'd coded a large enough sample. And here on the right, you can see the inter-rater reliability for each construct, each of which was above our initial criterion of 0.6, Cohen's kappa. We'll talk about that in a future lecture. We then extracted 100 features from each of the thinklets, thinklet being the term in CueThink for a math problem that you engage in this process in. This included features at the thinklet level, such as the number of questions answered in a thinklet and the number of questions answered in each phase, and also features at the level of phrases in student input, such as the number of words, nouns, verbs, numerical values, keywords in their textual explanations they generated. We used the ground truth data from 182 thinklets and features distilled from the same set of data. We trained models using XGBoost to predict the presence of the 5 SRL indicators, and we evaluated the model performance using 10-fold student-level cross-validation, which we're going to discuss in detail next week, but it's basically a way of cutting up the data and building models on part of the data, testing on another part of the data to make sure it's valid, and we computed the average AUC ROC, which, again, we're going to discuss next week, of each model. And I apologize for all the, hey, we're going to discuss this in the future. There's actually this really hard trade-off in designing a course like this about if you wait to give examples until you've discussed all the things an example needs to understand the example, then you wait to discuss examples until you're a third through the course. So do your best to follow along here and know that you may want to come back and rewatch this video after you've learned about all these terms. Results. A model could not successfully be built for strategy orientation, but the other models reached an AUC ROC above 0.75, which means that if you were to take a student who demonstrated a strategy and a student who didn't demonstrate a strategy and say, how often can the model tell which is which, the model could tell more than 75% of the time. And you can see on this graph the exact percentage for each construct. We then calculated Shapley additive explanations value, which we're going to discuss later on, of each feature in each model. And this is a way of determining which features are important to the model. And we found the most important 5 features in each model. We found that most of the features had to do with student behavior in the understand and the plan phases rather than the solve or the review phases. In specific, for numerical representation, it was particularly important whether students used numerical values in their answer, not shocking, and similarities between different responses. For contextual representation, it was the use of keywords specific to each problem and the length of the response. For outcome orientation, it was again the use of keywords, but different keywords in this case, and the use of numerical values. And for data transformation, it had to do with behaviors during strategy selection and again the length of the responses. We next checked these detectors for algorithmic bias, and in each detector, relatively small differences in AUC ROC were observed across different gender and racial ethnic groups, which served as evidence that our detectors were not particularly biased. In specific, no student group, either in terms of gender or racial ethnic group, consistently had the best performing detectors. So, as you can see, it's hard to discuss an example in detail without getting a little ahead of ourselves. So, why this example? First of all, we had theoretically grounded constructs that were based on Winne's model and that were important to teacher practice in this area. We had theoretically grounded feature engineering. The features that we chose mapped meaningfully, potentially, to the kind of constructs we wanted to detect. We had validated training labels. This wasn't just something that popped out of the sky, we'd actually demonstrated that human beings could agree on this. We had a modern classifier. We had appropriate validation and metrics. There was attention to interpretability. And finally, there was attention to algorithmic bias. Now, any couple of these you might find in just about any paper, but there aren't many that kind of follow this entire process from beginning to end of paying attention to quality and validity from beginning to end of the process. In the next lecture, we'll move on and go back to kind of a general family of algorithms, which is neural networks. Thank you very much.